Hello once again, class. Hope you're all having a fantastic day. Okay, so today we're going to be talking about applications of quadratic functions. And the most common one that we see is vertical motion. If you've had physics, this is probably a no-brainer. It's something you've dealt with quite a bit. H of t is the height of something. T is time in seconds. V is the initial velocity. So if you throw something or if you hit a ball or whatever it is, the initial velocity that it takes off with just goes right in here for V of 0. And S of 0 rather, is the initial height. So think about it, if you're hitting a baseball and you hit the ball 3 feet above the ground when it's being pitched to you, then 3 would go into here, the initial height of the ball. You know, all that kind of stuff. So, question here says, you are standing on a bridge over a river holding a rock 36 feet above the water. You toss the rock up with a velocity of 20 feet per second and watch it hit the water. Write a function which models the height of the rock over time. So obviously here, h of t is going to be, and this negative 16t squared, that's what we call the gravity constant. That's gravity pulling it down. And then plus, let's see, it's 20 feet per second, so that's 20t plus, and you're 36 feet above the water. And then it says graph the function over a reasonable domain. Well, there's the announcements. Fantastic. So it says graph it over a reasonable domain. So what I'm going to do here is grab my handy dandy calculator, punch it in, negative 16x squared plus 20x plus 36. And on my window, if you've ever thrown a rock over a bridge, the window could probably go from 0 to 5 seconds or so. It's not going to last any longer than that. Y min can be 0, and Y max, you're standing 30 feet and it says you toss it above, so it could go up. Let's just make it 40 feet and see what happens. I may need to adjust that, and I do need to adjust it a little bit. I need to get a little bit taller and not so wide. So let's take it to 3 and 50. Perfect. So here's what I'm going to do. I'm going to come over here and I'm going to graph it. So this is my time, and looks like I can break it up into 3 seconds. 1, 2, 3. And my feet, I can break it up into 10. So 10 feet, 20 feet, 30 feet, 40 feet, and 50 feet. And it says it starts at 36, right about here. And I need to come up with some information from my graph. So I'm going to find my 0, second trace, 0. I'm going to come over here, hit enter for my left, come over again, hit enter for my right. My 0 is 2.25 seconds. So at 2.25, that's going to hit the water. All right. And then I can find my maximum here. Second trace, 4 for my maximum. Let's say 0 and 1 should work. My maximum is 0.625. So let's say right about here, and 42. Right about here. Bam. Bam. So here's my maximum of 0.625, comma 42.25. And once I've got that information, I can answer all of the rest of my questions. So my domain is going to be 0 to 2.25. Obviously, it doesn't need to be any bigger than that. Good grief. Range is going to be 0 to a maximum of 42.25. When will the rock hit the water? Well, we already discovered that's 2.25 seconds. What's the maximum height? Well, that's 42.25 feet. And when will the rock reach its maximum height? That's going to be at 0.625 seconds. All right. So a lot of good information we can get out of this, and it all comes from just applying this formula to real world situations. So it's going to be a relatively short video today. Suppose that you just release the rock. So you're holding the rock and then you just let it go. And you let it fall into the water instead of throwing it. Write a function that models the height of the rock. So some of the stuff has stayed the same. The only thing that's changing is your initial velocity. You're not throwing it anymore. Now you're just letting it go. So instead of throwing it, you're letting it go. So that means that the middle portion here, initial velocity, is going to be 0. So it's just going to zero out your velocity and make your function h of t negative 16t squared, nothing ever changes with that, plus the 36 feet that you're up in the air. So the difference between this one and the front one is that this 20 becomes a 0 and gets rid of this 0t. So it's no longer there. So let's graph it and see what it would look like. Back on here, I'm going to go to my function and get rid of that. Graph it. So here's my function. Let's see, it's going to be a max of, let's go ahead and label these again, 10, 20, 30, 40, 50, and 1, 2, 3 seconds. This is time, this is height. Starts at 36. And in this case, we just let it fall. So let's figure out where this thing hits the water at. So second trace, number 2 is 0. Left bound, where's my cursor at? There it is. Here, right bound, go below until I see the y value getting negative. Enter, enter. So 1.5 comma 0. So 1.5, it's going to hit the water. So your domain is going to be 0 to 1.5. Oops, bracket, 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 bracket. Bracket, 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 bracket. Range will be 0 to 36. Because I'm not throwing it up now, I'm just letting it go. So obviously where I'm standing will be the max. When will the rock hit the water? 1.5 seconds later. What is the maximum height? Obviously 36. I'm not throwing it anywhere. I'm just letting it go. So my height is its maximum height. When will the rock reach its maximum height? Well, that's when I let it go, 0 seconds. How would the function change if you threw the rock toward the water at an initial velocity of 20 feet per second? See, if you read this other side here, it says that you toss the rock up. So you're throwing the rock up. Now, instead, you're throwing the rock down. So how would that change? Well, you have your height. Gravity will not change. See, gravity is pulling you down. That's the reason why it's negative. Now, I want you to bear in mind, this is not the constant of gravity. I'm not talking about 9.8 meters per second squared or 32 feet per second squared. I'm not talking about that. This is the quadratic equivalent of gravity, okay? This is not the gravitational constant. I just want to make sure because I know some of you are going, but Mr. Ballard, physics is a thing. And I know it is. I know physics is a thing. This is not the gravitational constant. This is just how it's represented as a quadratic. Moving on. You'd still be starting out at 36 feet, but with this initial velocity, instead of throwing the rock up, you're throwing the rock down. So it's minus. And then when would the rock hit the water? So y equals, let's change this to, I'm going to go second delete, gives me an insert option, minus 20t. And boom, man, it chunks it towards the water. I'm going to calculate my 0. I'm going to call my left bound 0.5, My right bound can be 2, and guess. You can manually enter in, when it says left bound and right bound, you don't have to scroll to click. You can manually push buttons in, push values in. And at 1, 0, so when would it hit the water? 1 second. So it's a relatively simple concept, especially if you've already had a little bit of physics involved. We're just talking about vertical motion, really. It's just vertical motion.